A series of earthquakes offshore southern Crete has once again drawn attention to one of the most tectonically complex and powerful regions in the Mediterranean. Within minutes of each other on June 20th, two notable earthquakes struck south of Kastri, Greece. The stronger event reached magnitude 5.2 at a depth of approximately 6 miles or 10 kilometers, while another magnitude 4.9 earthquake occurred nearby at the same depth. Their epicenters were located offshore, along a section of the eastern Mediterranean where immense geological forces have been shaping landscapes, coastlines, and human history for millions of years. Questions inevitably arise whenever earthquakes occur in this region. Are these events simply part of the Mediterranean's normal seismic background? Do they indicate heightened stress along a major tectonic boundary? Are they reminders of the enormous earthquake potential that exists south of Crete? And why does this particular stretch of sea remain one of the few places in Europe capable of generating truly giant earthquakes? The recent activity does not provide evidence that a major earthquake is imminent. Earthquake science does not currently allow precise predictions, and most earthquakes of this size remain isolated events followed primarily by aftershocks. Yet these tremors are significant because of where they occurred. Their location places them directly above one of Earth's most active plate boundaries, a zone where the African plate continues its relentless movement northward beneath the Aegean region. Every earthquake in this area serves as another reminder that the Mediterranean is far from geologically quiet. The epicenters were located south of Crete near the Hellenic Arc, a vast curved tectonic system extending across southern Greece. This region forms part of the boundary between the African and Eurasian tectonic domains. The interaction between these enormous sections of Earth's crust has been ongoing for roughly 50 million years, a process tied to the gradual closure of the ancient Tethys Ocean. The Mediterranean Sea visible today represents the surviving remnant of that once expansive ocean basin. The motion involved may appear slow when measured on a human timescale. The African plate advances northward relative to Eurasia, at rates ranging from approximately 1/6 of an inch to nearly 4/10 of an inch per year, equivalent to roughly 4 to 10 millimeters annually. Such movement might seem insignificant over a single year, yet over centuries and millennia it becomes immense. Rocks deform, faults accumulate strain, and eventually stored energy is released through earthquakes. South of Greece, convergence becomes even more intense. Along portions of the Hellenic subduction zone, tectonic motion reaches approximately 1 1/3 inches annually, or about 35 millimeters per year. In geological terms, this is exceptionally rapid. The result is a dynamic environment where compression, extension, faulting, and crustal deformation occur simultaneously. The recent earthquakes occurred within this environment. Their depth of approximately 6 miles or 10 kilometers places them within the shallow crust, an area where earthquakes are often associated with faults responding directly to regional tectonic stress. Determining the exact fault responsible requires detailed seismic analysis and focal mechanism solutions, information not immediately available following the events. Nevertheless, the broader tectonic setting provides important clues. The Hellenic Arc is not defined by a single fault stretching continuously across the region. Instead, it consists of an intricate network of structures that accommodate deformation, generated by the ongoing descent of the African plate. Some faults accommodate compression through thrust faulting. Others experience extension through normal faulting. Additional structures accommodate lateral movement through strike-slip motion. Together, they form an extraordinarily complex geological system. One reason this complexity exists is the phenomenon known as back arc extension. While the African plate dives downward beneath the Aegean region, portions of the crust above the subduction zone are simultaneously being stretched apart. This extension creates normal faults throughout Greece and western Turkey. As a result, earthquakes can originate from multiple fault types, even within relatively small geographic areas. The Mediterranean often appears calm at the surface. Popular images of blue waters, islands, tourism, and ancient coastal settlements can obscure the immense tectonic activity occurring below. Yet seismic records demonstrate that this sea remains one of the world's most active regions outside the Pacific Ring of Fire. The highest concentrations of Mediterranean seismicity are found along 3 major zones. The first is the Hellenic subduction zone south of Greece. The second is the North Anatolian Fault System in Turkey. The third is the Calabrian subduction zone in southern Italy. Together, these regions account for much of the seismic activity affecting southern Europe and surrounding areas. The Hellenic system stands apart because of its capacity to generate extremely large earthquakes. Geological evidence indicates that portions of the subduction interface are capable of producing earthquakes exceeding magnitude 8. Such events are uncommon, but the geological conditions necessary for them clearly exist. The distinction between moderate earthquakes and giant subduction earthquakes is important. A magnitude 5.2 earthquake releases substantial energy and is easily felt across a broad region. However, a magnitude 8 earthquake releases hundreds of times more energy. An event exceeding magnitude 8 can alter coastlines, generate destructive tsunamis, and affect vast portions of an entire sea basin. History demonstrates this potential vividly. One of the most significant earthquakes ever associated with the Hellenic Arc occurred in the year 365. Geological studies and historical accounts suggest that a massive earthquake struck near Crete with an estimated magnitude between 8.3 and 8.5. The event generated a powerful tsunami that affected coastlines across the Mediterranean. Evidence of vertical coastal uplift remains visible in parts of Crete even today. Ancient shorelines were abruptly raised above sea level, preserving geological clues that reveal the enormous forces involved. The earthquake became one of the defining natural disasters of the ancient Mediterranean world. That event continues to influence scientific thinking because it demonstrates that the Hellenic subduction zone possesses the capability to produce truly great earthquakes. Few regions in Europe share this characteristic. The recent earthquakes south of Kastri are nowhere near that scale. Nevertheless, they occurred within the same broader tectonic system. Every moderate earthquake contributes valuable information about how stress is distributed throughout the region and how faults are responding to ongoing plate motion. The modern seismic record further illustrates the Mediterranean's earthquake potential. The magnitude 8.2 Kythera earthquake of 1903 remains among the largest instrumentally recorded earthquakes in the region. Another major event occurred near Rhodes in 1926, with a magnitude of approximately 7.8. Both were associated with subduction-related tectonics. Elsewhere around the Mediterranean, devastating earthquakes have repeatedly struck populated regions. Along Turkey's North Anatolian Fault, a sequence of major earthquakes migrated westward during the 20th century. Beginning with the magnitude 7.8 Erzincan earthquake in 1939, several destructive earthquakes ruptured adjacent fault segments over subsequent decades. The sequence culminated in the magnitude 7.6 Izmit earthquake of 1999, which struck one of Turkey's most densely populated industrial areas. The Mediterranean's seismic history extends beyond Greece and Turkey. Southern Italy, Sicily, North Africa, Cyprus, and the Iberian Peninsula all contain records of destructive earthquakes spanning centuries. The region's long-written history provides an unusually rich archive of seismic events predating modern instruments. This historical perspective is important because instrumental records cover only a tiny fraction of geological time. Modern seismometers have been operating for roughly a century. Major tectonic systems evolve over millions of years. Consequently, historical records and geological evidence often provide crucial insights into the true earthquake potential of a region. The earthquakes south of Crete occurred in an area where several tectonic processes overlap. The primary driver remains subduction, with the African plate descending beneath the Aegean microplate. However, local crustal faults also contribute significantly to regional seismicity. These local faults are capable of producing earthquakes in the magnitude 6 to magnitude 7 range. Such events can cause substantial damage, particularly if they occur near populated coastal areas. Geological assessments generally place the upper range of local crustal fault earthquakes around magnitude 7 to magnitude 7.3. The larger threat, from a purely geological perspective, comes from the subduction interface itself. If a significant portion of the Hellenic megathrust were to rupture, earthquakes exceeding magnitude 8 become possible. Such events are rare but firmly within the geological capabilities of the region. The distinction between these earthquake sources matters because each produces different patterns of shaking and different hazards. Local crustal earthquakes often generate stronger shaking close to the epicenter. Megathrust earthquakes affect much larger areas and are more likely to generate significant tsunamis. Tsunami risk remains an important consideration throughout the Mediterranean. Although the sea is smaller than the Pacific Ocean, its enclosed nature allows tsunami waves to affect numerous coastlines in relatively short periods. Historical examples illustrate this danger. The famous Lisbon earthquake of 1755, estimated at approximately magnitude 8, generated a destructive tsunami that swept across portions of the Atlantic and impacted coastal settlements extensively. Although occurring near the Atlantic entrance to the Mediterranean system, it demonstrated the capacity of major regional earthquakes to create basin-wide effects. Another significant example occurred near Sicily in 1693, when a large earthquake generated tsunami waves that devastated communities along the island's eastern coast. The 1908 Messina earthquake produced both severe ground shaking and a local tsunami, contributing to one of Europe's deadliest natural disasters. The possibility of tsunami generation is one reason why large earthquakes along the Hellenic Arc attract particular attention. Significant vertical displacement of the seafloor can transfer enormous amounts of energy into the water column above, initiating waves capable of traveling across the Mediterranean. For the recent magnitude 5.2 earthquake, there is no indication of such large-scale displacement. Earthquakes of this size generally do not generate major tsunamis. Their significance lies more in what they reveal about ongoing tectonic activity than in immediate tsunami concerns. The clustering of earthquakes near Kastri also reflects a broader characteristic of active tectonic regions. Earthquakes often occur in sequences rather than complete isolation. Stress changes caused by one rupture can influence neighboring faults, producing additional earthquakes over hours, days, or weeks. Such sequences do not automatically indicate escalation toward a larger event. Statistical studies consistently show that most moderate earthquakes remain moderate earthquakes. While some eventually prove to be foreshocks, the majority do not. This uncertainty remains one of the central challenges in seismology. After an earthquake occurs, scientists can identify probabilities and assess evolving seismic patterns. However, distinguishing a foreshock from an ordinary earthquake generally becomes possible only in hindsight if a larger event follows. For now, the recent activity south of Crete fits comfortably within the established seismic behavior of the Hellenic Arc. The region experiences frequent earthquakes because tectonic forces there never stop operating. The African plate continues moving. The Aegean region continues deforming. Faults continue accumulating and releasing stress. What makes these events noteworthy is not their size alone, but their location within a tectonic system capable of producing some of the Mediterranean's most significant earthquakes. Modern monitoring networks provide a level of observational capability unimaginable to earlier generations. Seismometers distributed across Greece, Europe, and the broader Mediterranean record earthquakes with remarkable precision. Satellite measurements can detect subtle crustal movements measured in fractions of an inch or millimeters. Oceanographic instruments monitor sea level changes that might indicate tsunami generation. These technologies allow scientists to track the evolution of active tectonic regions in unprecedented detail. Yet even with these advances, fundamental geological processes continue operating according to timescales far longer than human observation. The earthquakes south of Crete represent only the latest expression of a tectonic cycle that began tens of millions of years ago. The forces responsible were already active long before recorded history and will remain active long into the future. Across the Mediterranean, mountains, islands, trenches, and volcanic systems all testify to the ongoing collision between major tectonic plates. Crete itself owes much of its geological existence to these processes. The island occupies a position directly influenced by the interaction between converging plates, making it one of the most geologically significant locations in Europe. The recent magnitude 5.2 and magnitude 4.9 earthquakes therefore serve as reminders of a broader reality. Southern Greece sits adjacent to one of Earth's major plate boundaries. The region's seismic activity is not an anomaly, but a natural consequence of continuing plate convergence, crustal deformation, and subduction. No evidence currently suggests that these earthquakes herald an imminent catastrophic event. Most likely, they represent another episode within the long pattern of seismic activity characteristic of the Hellenic Arc. Yet they also highlight why geologists continue to pay close attention to this region. The offshore waters south of Crete remain among the most consequential seismic zones in the Mediterranean. Local faults can generate damaging earthquakes. Larger sections of the subduction system possess the capacity for major regional events. Historical records, geological evidence, and modern monitoring all point to the same conclusion. Tectonic activity here remains vigorous, persistent, and deeply rooted in the ongoing evolution of the Mediterranean basin. As the African plate continues its slow northward advance and the Hellenic subduction zone continues accommodating that motion, earthquakes will remain an expected feature of the region. The latest tremors near Kastri are part of that continuing process, a process measured not in days or years, but in millions of years of geological change that continue shaping Greece, Crete, and the Mediterranean Sea today. One factor that makes the seismic activity south of Crete particularly important is the structure of the seafloor itself. The Hellenic Trench, which forms part of the broader Hellenic Arc system, is not merely a line on a tectonic map. It is a vast geological feature extending for hundreds of miles and hundreds of kilometers across the eastern Mediterranean. Along this boundary, the oceanic crust associated with the African plate bends downward and begins its descent into Earth's interior. As the plate sinks, enormous stresses accumulate both on the plate interface and within the descending slab itself. Rocks that appear rigid on human timescales are actually capable of bending, fracturing, and deforming when subjected to geological forces over millions of years. Earthquakes occur when the accumulated stress exceeds the strength of the rocks, allowing faults to rupture and release stored energy. The recent earthquakes near Kastri occurred at a relatively shallow depth of approximately 6 miles or 10 kilometers. This is significant because shallow earthquakes tend to be felt more strongly at the surface than deeper events of similar magnitude. In contrast, earthquakes occurring dozens or even hundreds of miles below the surface often distribute their energy across a much larger volume of rock before it reaches populated areas. The eastern Mediterranean contains earthquakes across a wide range of depths. Some occur within the shallow crust, while others originate deep inside the descending African plate. Seismic studies have detected earthquake activity extending to depths greater than 186 miles or 300 kilometers beneath portions of the region. These deep earthquakes provide evidence that the subducting plate remains relatively intact as it descends into the mantle. The existence of such deep seismicity highlights the immense scale of the geological processes operating south of Greece. The recent magnitude 5.2 earthquake may have occurred close to the surface, but it was connected to a tectonic system extending far below the seafloor and deep into Earth's interior. Crete occupies a particularly strategic position within this system. The island sits near the outer edge of the Aegean region, directly north of the active subduction boundary. Geological studies show that Crete itself has experienced repeated episodes of uplift over long periods. Ancient marine terraces preserved above present sea level indicate that portions of the island have risen significantly through time. These elevated coastal features serve as geological records of tectonic activity. In some locations, former shorelines now stand many feet and several meters above the modern sea. Such uplift reflects the long-term deformation associated with subduction and major earthquake cycles. The landscape visible today is therefore not static, but the product of countless episodes of crustal movement accumulated over thousands and millions of years. Another important characteristic of the region is the relationship between seismic activity and volcanic activity. Although the earthquakes south of Crete are not volcanic earthquakes, the broader tectonic system has created conditions favorable for volcanism elsewhere in the Aegean. As the African plate descends, water and other volatile compounds are carried downward into the mantle. These materials lower the melting temperature of surrounding rocks, contributing to magma formation. The result is a chain of volcanic centers extending across portions of the Aegean region. This process explains the presence of volcanic islands and volcanic fields within Greece. The most famous example is the volcanic system associated with Santorini, whose ancient eruption ranks among the most significant volcanic events in Mediterranean history. Although volcanic hazards and earthquake hazards are distinct phenomena, both originate from the same large-scale tectonic framework that governs the region. The interaction between earthquakes, crustal deformation, and volcanism demonstrates that southern Greece is part of an active geological environment rather than an isolated seismic hotspot. Every component of the system reflects the continuing convergence between major tectonic plates. From a long-term perspective, the Mediterranean itself remains a basin in transition. The collision between Africa and Eurasia has already eliminated vast portions of the ancient Tethys Ocean. Mountain ranges throughout southern Europe, including many located far from present coastlines, were ultimately shaped by this prolonged convergence. The process continues today. Although plate movements measured in millimeters per year may appear insignificant, they represent a continuation of forces capable of reshaping continents. Over 1 million years, a movement rate of approximately 1 1/3 inches annually or 35 millimeters per year translates into more than 21 miles or roughly 35 kilometers of total displacement. Such figures help explain why earthquake activity persists generation after generation. The tectonic engine driving the region never truly stops. Stress is constantly being introduced into the crust, ensuring that faults remain active over geological timescales.